All right, you might be wondering why there's a person slipping on the ice, and that is because nobody has salted it. This is Properties of Solutions, and it is part 3. There will be a part 4 as well by Mindy Bedrosian. All right, this time we're looking at colligative properties. When a solute is added to a solvent, the properties of the solvent change. That's what happens. And actually, it doesn't even really matter what exactly is added to the solvent. Just add something to it, and the properties will change. So let's pretend we have a beaker that's covered and with a solvent in it. And the dynamic equilibrium is reached. Certain numbers of molecules are leaving the water, and certain numbers of molecules bump back into the water and leave the gas phase and enter the liquid phase. So there is a dynamic. Some are leaving, some are coming back. When a solute is added to the system, however, there are 3 major changes that happen. We're going to take a look at that. Let's draw this picture again. And let's add a solute to this solvent. So the first major change that occurs is the vapor pressure above the solution is lowered. A non-volatile solute is added, meaning it does not turn into gas very easily. It interferes with the solvent. It breaks up the intermolecular forces and annoys the entire system, so the solvent cannot evaporate as well. So less molecules can enter the gas phase above the liquid. So there will still be some gas molecules above, but less of it can escape. The extent this lowers the vapor pressure is proportional to the concentration of the solute. This can be expressed by using something called Raoult's law. The partial pressure of the gas is equal to the mole fraction times the partial pressure of the gas, of the pure solvent rather, not the gas. So this is PA is the partial pressure of the solvent above the solution. XA is the mole fraction of the solvent in the solution. And P prime A, that's called the prime, is the vapor pressure of the pure solvent. Usually you get that from a table. So let's do an example with Raoult's law. We're going to take some glycerin, there's the formula. It is non-volatile, and we're going to add it to some water. It has a density of 1.26 grams per milliliter at 25 degrees Celsius. We're going to calculate the vapor pressure at 25 degrees Celsius of a solution that was made by adding 50 milliliters of glycerin to 500 milliliters of water. So you may just stop now and try it yourself. You probably need to know the vapor pressure of pure water at 25 degrees Celsius is 23.8 torr. I'm going to break this up into steps. You can pause and try it. Otherwise, you can stop after each step. So for step 1, you would have to find the moles for glycerin and water. You can stop or continue. Here is the answer for the number of moles for the glycerin and the number of moles for the water. 0.684 moles for glycerin, and for the water it's 27.8 moles. You can continue or pause, and here comes step 2 if you haven't paused. Step 2, you're going to calculate the mole fraction of the water. That is the solvent, so do that. And here's the answer coming if you haven't paused. So X water mole fraction would be 27.8 moles of water over both of them added together. So the moles of the glycerin plus the moles of the water will give you your mole fraction. And the answer is coming. And here it is. Step 3. So for step 3, use Raoult's law and plug in these numbers. We know the vapor pressure of pure water, so you should be able to find the vapor pressure of the solution. That would be plugging it in, plug in the numbers, and here's the answer. 23.2 torr would be the vapor pressure. Please note that the vapor pressure has been lowered from the pure solvent by 0.6 torr compared to the pure water. This is the end of part 3, and we will continue in part 4.